It was originally Johannes Harding was going to give it, and he is a PhD student here in the department. But when he then couldn't do it, we took the opportunity. So with me here I have Jan Magne. He is a PhD student, but also head of Earth Lab. He is doing a lot of CT work, so he's going to present a little bit his work on how to use a CT scanner to detect floods. And then I have here Associate Professor Paul Nielsen, and he has been working on this exciting record, 11-meter long record from Vangsvatn in Voss, close to Bergen. So I'm going to do an introduction, and then I'm going to give the word to Jan Magne and then to Paul. So just to show you this topic, it's very relevant nowadays. Just for the news today, in Spain there was a flash flood, 51 people killed, very dramatic. And then we have this extreme warning for Western Norway. It's forecasted 180 millimeter in the next 24 hours, which I think is actually some of the worst forecasts I ever have seen. And it's an atmospheric river called Jakob that is going to hit us, in the next 24 hours. So they expect some records, especially like in the fjord area of Norway, Western Norway. Yeah, so that was just to show you where we are. And I just want to also remind those of you who are not familiar with this Norway topography, that we have this mountain range that is a barrier for the westerlies. It's an extensive mountain range, 2,500 kilometers long, and it creates an amazing gradient from west to east when it comes to precipitation. The highest peaks are up to 2,400 meters, Galdhøpiggen. And I took this little figure down in the right corner to show the difference in the drainage patterns from the west to the east. In the west, it's a very short way from the mountains to the fjords. In the east, it's a long way. And especially for spring floods, snow melting floods, that's very important because they builds up, an enormous momentum when they are going to the ocean, and with a devastating effect. So of course I don't need to present this for you. This is basically showing the water transport in the atmosphere, made by some colleagues at the Bergen Center in the fall of 2014, when we had these big hurricanes coming out of Gulf of Mexico. They just illustrate, Scandinavia, its place, in this global system, and the mountain range that we have here, receiving a lot of precipitation from the west, hitting the mountains, creating this gradient I'm talking about. But it also may create some kind of non-stationarity in this system. We have the North Atlantic Oscillation that is a very important feature in the winter time here. So we expect kind of a lot of variability in this part of the world when it comes to hydroclimate and precipitation. So that's part of the story here. And then on top of this, of course, we have the effect of global warming that changes things for us. So just as a backdrop, in July 1789, we should actually take away that, there was a big flood in Norway, the biggest we know about, also in the paleo records. And it was a combination of an atmospheric situation and a melting event, because this was during a little ice age. So it was a year with a lot of snow in the late spring, permafrost in the ground in the mountains. And then we had this very interesting atmospheric situation that reconstructed on this map. This is hand-drawn, as you can see, but it's based on pressure observation from boats, basically. And you see that the situation here was that you had like low pressure here, low pressure building up here over UK, and then they kind of merged, and then there was another low pressure system up here north of southern Norway, and that led to actually that you had like a transport of humid air that was blocked over central Norway, and it created this crazy flood. You can see the flood marker here, it's up here, 22nd of July 1789. It's the highest level we had in eastern Norway. We had one in 1995, but we couldn't even match that. So that's kind of one of the most devastating floods we know about, also confirmed by our pilot records. I'll come back to that. And then last year in July, we had another extreme events, but no, I mean, here you see the precipitation in the central part of Norway, 150 millimeter within 12 hours. So it's quite similar to actually what is forecasted for us now. But this was a very devastating flood in Norway, and a lot of damage. So far, the damage has been calculated $150 million, mainly because there was a lot of avalanches, soil avalanches, in very unexpected areas, in lowland areas, but also a lot of damage to the riverbeds, like you see here, and they have to rebuild it. And only this little piece of the river here is 300 meters. It costed about $7 million for only this little piece of the river. So this is have huge consequences. And then we're also facing a situation now where we have melting ice caps, as you all know, all over the world. But in Norway, it's also special because these ice caps are plateau glaciers. People are living around them. And when they melt, they could create dangerous situations, and they could be also the starting point for so-called compound events. If you combine like an extreme rain event with melting of the glacier and maybe also a glacier dam lake, then you have the perfect scenario for disaster. So this is also part of what we are facing here. Yeah. So what we have been working on is to try to put this present day increased flooding into a longer time perspective. And this is something that not only we here in Norway is working on, this is people working on all over the world. And I think it's important to have extended instrumental records of flooding. Normally they go back maybe 100 years. And we would like to work on try to expand that and get a longer time perspective on the frequency distribution. And there was a paper by Kolben Egeland, is a hydrologist in NVE, some years ago, together with some of our colleagues who see here, Eivind Stør, for example, he was working here before, Eivind Påske. They did a lake-based reconstruction of floods in a lake called Flyvingdalsvatnet in eastern Norway. And Kolben, he used the data to look at the flood frequency and to look at how they calculate the recurrence interval. And he also recognized this non-stationarity in the 200-year flood. You can see there are certain time periods where you have more of these floods. And this is, of course, especially worrying in future warmer climate, So we have been working with lake sediments. We're using lakes for a lot of things, but in this case, it's about flooding. And then, first of all, the site selection is key, to get a site where you actually have a flood signal which is purified. Lakes are a trap for all kinds of sediments, so it's important to look into what kind of processes that are actually affecting the sedimentation in the lake. So this is just an illustration that Johannes made based on some, I guess it's one of your figures, Willem, or? Yeah. So, but it's nicer, isn't it? But anyway, it shows kind of how complex these lakes are. They are influenced by avalanching and glaciers in the catchment, all kind of things. And if you want to have a good flood lake, you should avoid as many of these processes as possible. And then we have been looking into the possibility of making frequency reconstructions, but also seasonality and magnitude. And that's kind of what we're going to talk a little bit about today. So this is just showing some of the records we have from southern Norway. It goes back with Atle Nesje's first work in Atnasjøen in 2001. A lot of other works. Christian Vaskog up here in 2011. A lot of master students from Bergen here. And some records from eastern Norway, the Flyvingdalsvatnet here. And I'm going to show you two papers today by Johannes Haveng from southern Norway. So we kind of got a nice spatial coverage of southern Norway, which is interesting. And Paul, he is working here, Tvangsvatnet. So hopefully at one day we can put all this together. and we can get like a more holistic view on what kind of frequency, seasonality, and magnitudes of floods we have through time. So I just want to, I'm not soon handing the word over, but these two papers are Johannes' paper from southern Norway, and one of them is looking into seasonality, which I think is a very interesting concept, and the other one is using a threshold lake to look into magnitude calculation of the floods. Just show a few figures for them, but you can also read the papers. So the main thing here, the site selection is important, and in this part of Norway, there's hardly any coverage of superficial deposits. It's all like bedrock mostly, but the valleys are filled up with glacial fluvial sediments. So you've got a very purified signal when you have floods eroding here. And then the magnitude concept here was based on this situation where you have two lakes that are situated close to each other. And when you raise the water level here in this lake, you basically reverse the flow direction. So this normally don't receive any water from the main river, but then when you flood, you got deposits of flood deposit, and then you can calculate the magnitude of the flood. I'll come back to that. So this is basically what Johannes has been working on. How you see this, the setting, the river comes in here, and then you have this other lake, which is a threshold. And we are taking course in both these lakes and use that for magnitude calculation. And they also did some simple modeling just to calculate how much water you actually need. So this is based on a 200-year flood, and then you see that you actually have quite a heavy velocity of water coming into to this lake. But this is rare though. But if you do a 200-year flood, then you really change the boundary condition for that lake. And one of the things Johannes was working on, maybe you will say something about that also, Paul, I don't know, but flood seasonality, he was using the instrumental record here. This catchment have about 100 years of instrumental data, because these sediment cores, they had like a very distinct two types of layers. They had mineralic layers, but they also had these plant-dominated layers. So Johannes had this idea that there might be a seasonality signal in that, like that the mineralic layers are more linked to the rainfall floods, and the plant dominated layers are linked to snowmelt floods. And he tried to link that with the instrumental record, and he actually did it was a good match on this. So that was quite interesting. And then taking that backwards down in the paleo record, it kind of shows that it's possible to look into seasonality in flood when you have a rain-dominated regime and when you have a snowmelt-dominated regime. And his summary figure from that paper is this, where you see that during you have the same type of floods all over through the record, but it's more dominant during the Holocene thermal maximum. You have warm summers, you have more of these rain-dominated floods. And then as you go into the neoglacial, you clearly see that it's more of these snow melting events that are occurring. So this is kind of interesting, and I think we're going to come back to this in the end after Paul and discuss a little bit more about how this is connected to the general Holocene climate regimes throughout the Holocene era. Now I'm going to give the word over to Jan Magna. Yes, talking about how to use the CT.
Yes, we have been using computer tomography, so CT scanning, quite a bit on sediment cores over the last 10 years or something here in Bergen and also other places. And we've used it quite extensively now on flood records. So for those of you who are not familiar with the CT scanner, it's an X-ray machine taking X-ray around an object, most commonly used in a hospital, where the patient is laying still and the X-ray source and detector is moving around. We have one that's built for sediment cores, looks like this inside, not as fancy as the one in the hospital, or not as clean, but it's better and give more high resolution images, and can also scan at higher voltage and current. So we place a core inside like this, and the core is actually spinning instead of the whole instrument. And this allows us also to zoom in on the objects we scan. So why are we doing CT scanning on sediment records? Mostly it's to allow us to see what we can't really see with the naked eye. It's also non-destructive, so we don't have to dig around in the core to actually see anything. It only shows density differences, but for sediment records, it has shown that a lot of things in a sediment core is actually also density differences, and the density differences can be quite small. So here you see a typical like 2D image from the CT scanner. It's called an autoslice, and it shows dark and bright light layers, which is difference in densities within this sediment section. And since we have a stack of these images, we can create 3D models as well, such as this, which is a marine core, but it shows nicely everything you can encounter within sediment core. So you have shell fragments, for instance, which has a higher density than the surrounding sediments. You have bioturbation, which is something you would normally not see, because if you start to dig around in the core, you will actually destroy it. And it's basically porosity differences within the sediments that makes it possible to see it in the CT scanner. So what we've done with this on sediment cores is that for floods, is that we've tried to isolate the flood layers from the background signal. So here we have a photo of a sediment core. This is actually one of the sections Paul is gonna talk more about later. And then we have the CT image underneath, which is gray and white and black. And you can clearly see some of these features on both images. Here you have sandy layer, you have some more organic layers that's brownish. But in general, you see a lot more on the CT scan because it highlights the differences better than a normal photo. Further, we've segmented out the two different types of layers. We have mineralogic layers, which has a higher density than the background sedimentation. And then we have organic layers, which has a lower density than the background sedimentation. So that's mostly plant fragments and so on. And the way we've done it in this case is actually to manually go in and isolate one of the like clear horizons and use that as a benchmark for when the threshold for, say, the mineralogic layer, and the same for the organic layers. Since we have this in 3D, you can also start to zoom in, and you can start to also pick up on like single twigs and other objects in the core that you might need to remove later on because they could create some artificial layers. The next step in actually creating a record out of this, and not just a fancy image, is to measure the volume percentage of the core that's actually covered. So what's done here is that downwards in the core, it measures how much of the core in area is occupied by either the yellow or the red, and gives that as a percentage. So a thick, distinct layer like this you would suspect it to give 100%, but because there is some porosity in between it, it will give a lower percentage. But as you can see, the clear horizons now show up as distinct layers. There is one problem with this method, and that's something called partial volume rendering, which is a huge problem we often encounter. And that's actually if you have, like in this image to the left side here, a gap of air. The border between the air and the sediments will actually show up as the same density as organic material. So to start off with, on the course Paula are working on, we actually had a lot of like false areas with material that showed up as organic material because of this effect. And the way we did remove it was to isolate the air and then artificially expand the air to include the border and then delete it from the data set. So yeah, you can see this on the figure to the right, where you have a small porosity air pocket within sediments, and you see it's air in the middle, and then it's like we've expanded it to also include the transition zone. What should we do? Very quick introduction to your method.
Yeah. Well, then I will continue with the work on the sediment course from Vangsvatnet, which is basically one of the sections that Jan Magne showed. And this is preliminary for now, but we are writing up an article based on these data. So it's basically trying to give the flood frequency of Holocene floods from Vangsvatnet here in Western Norway. So Voslo catchment has a really long history of flooding, and it has well-known events dating all the way back to 1604, and also I think one of the longest records in Norway for measurement instrumental data back to 1892. And we know that the Vosso River has a biannual flood regime. There are persistent low pressure systems that leads extreme rainfall events, such as the one tomorrow, resulting in substantial water discharge in the river. But more than 50% of the river catchment are also quite high altitude, and it drains large mountainous areas, which normally accumulates a lot of snow during the winter time. So there are also snowmelt floods during the spring. So we have 2 floods a year always. And the goal for this project is to reconstruct the flood frequencies throughout the Holocene and also shed light on some connection between floods, the climate variability, and also current extremes in the catchment today. Just to give an introduction where we are. So we are now in Bergen, and Voss is situated around 100 kilometers eastwards from Bergen, still on the western side of the main watershed. And the Vosso catchment is one of the largest river catchments in this area of Norway, drains around 1,000 square kilometers. And on the right-hand side, we see a map of the current annual precipitation. So it's an area with around 1,500 millimeters of precipitation during a year. And models are also assuming an increase in precipitation in this region up to 30% the next 50 to 100 years. So it's an important region and will also be a change in floods for the next 50 to 100 years here. So more knowledge on past floods are needed. And zooming in to the catchment, here is the village Voss, and the dark blue lake here is the Vangsvatnet, where we took the core. And the area is actually affected by 3 rivers that are actually entering the Vangsvatnet. So 2 of the rivers, Strandelva from the north and Reindals and Elvi from the east, are coalescing at the city center and forming the Vosso River entering Vangsvatnet on the eastern side. There's also a small river coming from the south, which is called Bodalselvi, which drains around 100 square kilometers. It is a quite smaller river compared to Vosso. Just to show you an image of the lake. So this is the easternmost part of the lake. The river here is the Bodalselvi, so the river from the south, while Vosso is coming along here and entering the lake approximately here. So this is an active delta today. And one important part of the Vosso catchment is the really narrow outlet of the Vangsvatnet. So this is the western part of the lake with a really narrow gorge going towards the west. So every time there is high discharge or floods, the lake gets filled up and the lake level actually increased quite a lot. So during the recent floods in 2014 and 2022, the lake level rised by around 7 meters in 1.5 to 2 days. And this figure here shows the instrumental record from Bergen, so the same area as, so near the outlet of Vangsvatnet. We also see there is a lot of floods going back to 1892, but with an increase in magnitude and frequency the last 30 years. So the two largest river floods in Vosso were actually in 2014 and 2022. You have to go back almost 100 years to 1918 to get almost a similar event. And one of the things they did that was, I think I have an image later on, but just to show you, this is from the flood in 2022, flooding a lot of the area around the village. So this is the sport arena, brand new after the flooding from 2014, and it destroyed, so they actually had to build new football field afterwards because it's not grass, it's plastic. Yeah. And just to show you the river at Langabrua in the city center during flooding in 2014, and normally the bridge is like this, so there is, I think, 3.5 meters of water coming through the bridge here. And so for the historical floods, here we see that there are a few water levels here of the lake. So in 2022 and 2014, the water rose 7 meters, while in the reconstructed 1604 event, the lake level was actually 11 meters. And in the 18th century, you had quite high flood levels. And due to this, they actually did a work in the outlet. So they lowered the lake level in 1865 and widening the channel from Vangsvatnet. And they did the same in the 1990s to reduce the flood in Voss. But still, in 2014, we had almost more than 800 square meter per second coming into Vangsvatnet and filling up to 7 meters above the low stand of the lake. And they've done a lot of modeling of the area, and on 200-year flooding, they will actually expect that large parts of the city or the village will be flooded. Also, a housing area on one of the sides of the Vosso River. And just for showing you the historical mark on the church, it's marked as 1604, and it was a flood during the spring, so a snowmelt flood. So then, talking a bit about the sediment record. So this map shows the lake. It's around 60 meters deep, the deepest part, and the core is retrieved around 400 meters from the delta at around 55 meters depth. And you also see the situation in the city center here with a lot of glacial fluvial sediments, which are easily eroded by the river during flooding. And there is done a lot of coring in this lake starting in 2016. And the last coring expedition we had here was during a course in 2022, a month before the flooding event in November 2022. So we have, I'm not sure, 10, 15 cores from this lake, varying from short gravity cores to long re-entry system cores, so up to 11 meters long. So in this talk, I'm going to talk about two of the cores that has been retrieved. So the gravity core retrieved in 2016, which is the uppermost section of the lake sediments, going back 85 centimeters. And then we have a re-entry core, which is the long one here in 6 sections, going 10.4 meters down in the sediments. And we also have an overlap with the gravity core at 70 centimeters. So as a composite, the core is more than 11 meters long and is dating back 8,500 years. And here is our quite nice HDAT model. It's based on 22 C14 dates from the long core and 1 lead 210 date on the gravity core, the uppermost 39 centimeters. And as we can see, it's quite stable sedimentation actually. It's increasing in the top mode, but we have a resolution of 1.8 to 40 years per centimeter. And this is just an image of the gravity core where we can clearly see these layers that Jan Magne already talked about in the CT images as well. And by looking at the lead-210 dating, we can actually pinpoint the age of these events and also relate them to the instrumental record. So here are some of the core data. We have XRF data and magnetic susceptibility data. We have loss on ignition. We have CT scanning, the whole core, and we have also quite a lot of grain size measurements. And on the right-hand side, you see the CT, or the density data. We see MS data, so it's quite high in the uppermost parts of the core and quite stable in the middle section and also quite high magnetic susceptibility in the lowermost part, while the XRF data are quite varying, but with clear spikes in the layers, the mineralogic and organic layers. And in the lowermost part, we see a lot of these 167 dots, which are the bulk samples that we have prepared for grain size analysis. And you can see some of the results on the lower left figure. So here we have actually divided it into background sediments, mineralogic layers, organic layers, and mixed layers. And we can see that they are quite varying. So the mineralogic layers are coarser than the background sediments. It's the same for the organic layers. They are also higher in organic material. And we have the mixed layers, which are in both organic and mineralogic, and are usually also thicker layers in the sediment core. Here are just a zoom in of the CT data. Jan Magne has already talked about the data, but here we can also look at the CT data together with the XRF data. So we see here that these yellow are the mineralogic or sandy layers, while the green ones are the organic layers. We see that the density, calcium values are high in the mineralogic layers, while iron are low in the mineralogic layers. We can also see the volume percentage here on the right-hand side. So when doing this CT analysis of the whole core, we get spikes in these mineralogic layers and also spikes in these organic layers. So by choosing the 90 and 95th percentiles of these data, we are building a flood reconstruction based on the CT data. And by doing this, we have recorded 167 of these mineralogic events and 94 of these organic events. And putting in or placing it in time, we can actually see every floods per 100 years here in this right-hand side image. And we also think that this river have these biannual floods. So the regime is quite similar to the site which Johannes worked at Lygne. So we think we have the same seasonality here at Voss. So during the spring, with the snow melt related floods, we have steady melting in April, May, June, so quite slow increase in discharge and lake level. And we think we have mostly transportation and deposition of organic material. So all the organic layers, most of the organic layers, we interpret as spring floods. While during the fall, we have these precipitation-related floods. And for example, in 2014, we had up to 250 millimeters in a few days. And during these events, we have a rapid increase in river discharge and lake level. And so erosion and deposition of mineralogic sediments in the lake. So by following this reasoning, we see that the dark gray bars here are the mineralogic or precipitation-related floods, while the light gray are the organic layers and snowmelt floods. So back in time, we can see that there are some transitions here in the data. So in the early to middle Holocene, we had mostly precipitation-related events, and with then kind of a change around 3,500 to more snow related events or snow spring floods. And around 1,500 years ago, we see a rapid increase in flood events in Vangsvatnet, both precipitation related and also snow related events. And during the Little Ice Age, which is this bar with 15 events in 100 years, we see mostly snow melting events, which are following some of the other data that we also have. So to try to put it in the context to Johannes Hardeng's figure, we see here the snowmelt and rainfall dominated events at Lygne. Comparing it to the North Atlantic Oscillation, this is a proxy to ELA reconstructions from Nordfonna, Jostein's work, to snow avalanching, both from Otto Nesje and Christian Vasskog, and also floods in east central Norway, which are normally or mostly snow-related events. And in the lowermost section here, we see the Lake Berse record from Johannes' last study from 2024, with the Vangsvatnet record plotted in the same figure. And there are some spikes that are not similar. We are working on interpreting our results from Vangsvatnet, but we see a large increase during the Neoglacial and towards the Little Ice Age, with more snow-related events marking this top. But we also have some periods without any floods, which are also quite interesting in Vangsvatnet. So, do you have any more to follow up here, Jostein?
We can take some good questions, I think.
Yeah.
So maybe just so you can see everyone.
Thank you very much. It looks pretty alarming for the next 24 hours or so, but I hope everybody stays safe. We now open it to questions, and we usually start with Bergen, so perhaps people in the room there would like to ask questions.
Yeah, is there any questions in the room? Jarle, you always have a question, huh?
Yes.
Come forward here.
Okay.
You have to talk in a microphone.
Yeah. Yes, I have a question for Paul. So you showed you showed the core and correlated the layers with historical flood events, but you didn't find a flood layer for that 1604 event.
No.
Where is it?
That's a really good question. So in our record, we can't find all of the historical documented floods, and so we have a minimum record, or we do not have all the floods. We have several cores. We can't identify all the same layers. So I think there was deposition of sediments in different areas of the lake at different times. So why we do not have the 1604, it's not certain. It could also have something with the configuration of a high water level during the flood. So we do not have a lot of erosion, for example, during an event. So not all events deposit layers. So that's I think it's a quite normal problem in several of these studies.
Thank you.
Any other questions from the room there?
No, I don't think so.
Okay. We'll open it to the group in general then. Any questions from the assembled people? Just speak out.
Yes, I would have one. Thank you so much for a super nice talk. And I just needed to put on the same jacket as Ray had. I just thought that he's wearing this jacket. I was wondering about the rationale for the higher flood frequency during the Little Ice Age in your sediment reconstruction, because you say that this is more due to snowmelt. And how can you prove this?
Also a good question. Well, it's based on the layers of both the organic and the mineralogic layers in that period. So it increased, both are increasing during the Little Ice Age. And so it's mostly, that's why. But we also know from other records in the area that there are more snow, or the snow are laying for longer, and maybe later on you have the floods, so in May and June instead of April or May. So it could also be larger floods during the Little Ice Age compared to at present.
Yeah, thanks.
Okay. Any other questions?
Steve Coleman here. I'm wondering if you see any evidence for non-flood sedimentation events, like a landslide in the catchment or turbidity currents off the front of the delta that are not associated with a flood.
That's also a really good question. We know we have really good bathymetrical data from Vangsvatnet, and we see that there's been some landslides occurring along the borders of the lake, but they are quite far from the coring site. And we also have chirp data from the lake. However, the chirp data from the easternmost basin are disturbed by a lot of gas in the sediments. So we can't actually penetrate quite far into the sediments. But we haven't encountered any turbidity currents or turbidity layers in the sediment core itself. But of course, some of the thick section could be a landslide from the delta front, but we haven't seen typical structures showing that.
Okay, I have a question. You have discharge data going back to the 1890s. Do you have sediment flux measurements? And do you have any sediment traps in the lake currently?
No, unfortunately, we do not have any sediment traps in the lake at Vangsvatnet.
Well, there's still time. You got about 12 hours to get out there.
That's true.
So, okay. Any other questions from the group?
Yeah, a quick question. Gifford Miller in Colorado. I'm wondering, one of the things we think about here are rain on snow events as giving the most extreme floods. And is that something sounded like you tend to think of the snow events as more gradual melting, but have you thought about how you might get a more extreme event if you have rain on snow.
Yeah, that's a good. I guess the combination of both snow and rain are the largest floods here in this record, and we have the so-called mixed floods, which are only occurring in the late Holocene in the record, but they are all only 12 or 14 events, and they are also the thickest events. And they are both combining organic and mineralogic sedimentation in the lake. So it could be some combination floods with a lot of precipitation on snow. Even we know that there are floods in December, quite late in the season, so it could be extraordinary warm periods with atmospheric rivers coming all the way into Voss and melting some of the snow that's already stayed there. So of course that could be one idea.
Okay, really nice study. Thanks for that.